morning, ladies and gentlemen. My name is Muhammad Ilham Bayquni, a research assistant from National Research and Innovation Agency, also called BRIN. I am pleased to have an opportunity to take part in Science and Technology Research Symposium or SiRes 2022, especially in material engineering topics. Here I represent my colleagues from BRIN to deliver the results of our research entitled Thermoluminescence Properties of Dysprosium calcium sulfate, synthesized by wet chemical synthesis route with pH adjustment. Thermoluminescence is a phenomenon of light emission from a solid material by thermal stimulation after energy absorption from ionizing radiation. This phenomenon is commonly used for dose measurement. Various insulators and semiconductors have been developed as TL materials. Due to the high sensitivity, simple glow curve, and relatively low fading, calcium sulfate-based phosphor is very suitable for dosimeter applications. Many authors have suggested various techniques for creating calcium sulfate phosphors, such as coprecipitation, acid recrystallization, mechanical alloying like ball milling, solid-state diffusion, etc. The wet chemical synthesis method were preferred as the low-cost and simple method, and it doesn't need any special instruments. Several factors affecting the quality of the phosphor, such as the type and the concentration of dopants in the host lattice, and also the particle size of the matrix. The particle size itself is dependent on the manufacturing process, so controlling variables such as precursors, acidity, reaction time, and calcination temperature is important to obtain desired particle size. In this work, we investigate the properties of dysprosium calcium sulfate TL material, and dysprosium was introduced as the luminescent center at certain concentration. This work serves as preliminary study for our research group to obtain TL material regarding the application of low-dose measurement. The calcium sulfate powder was obtained through a wet chemical synthesis route referred to Kadari's work, using calcium chloride dihydrate and sodium sulfate anhydrous as precursors, and dysprosium oxide was used as dopant material. The synthesis was initiated by dissolving all precursors in mixed solvent, consisted of distilled water and ethanol in ratio 1:2, followed by dissolution of dysprosium oxide in sulfuric acid. Then, all solutions were mixed together. The pH value of the mixture was then adjusted to 5 by the addition of ammonia and stirred for 3 hours to obtain a white viscous mixture. The mixture was dried overnight at 90 Celsius degree and calcined at 650 Celsius degree in an air atmosphere for 4 hours to obtain the dysprosium calcium sulfate powder. A few mounds of distilled water were used to wash the powder after the heat treatment. A scanning electron microscope was used to observe the particle morphology of the powder. The elemental composition of several spots was also conducted using the instrument with the DS detector. An XRD was used to identify the phase composition of the powder, and the obtained diffraction patterns were then analyzed using the Pananalytical ICSD database for high score. The DXRF spectrometer was used to measure the dysprosium content of the powder. Analysis of the thermoluminescence profile was carried out using the Herschel TLD reader after a low-dose beta exposure from strontium-90. The particle morphology observation was conducted after heating at certain temperatures, as shown here. Some of the powders were solidified after calcination, hence a manual grinding was carried out for a while to crush the brittle bulk solids into smaller particles using mortar and pestle. Agglomerated fine particle solids were observed for both samples, though the particle size still varies since there was not any further sieving after grinding process. Smaller particles were found at lower heating temperature, presumably due to the existence of an amorphous compound containing carbon that may come from an organic substance that is ethanol as measured using an ADS detector. The calcined powder exhibited a prismatic crystal shape. The EDS measurement was used to analyze the elemental composition of a certain area in the BSD image. The atomic concentration of several spots marked by A till D was summarized in this table. The spectroscopy analysis showed the expected elements of base material, that is calcium, sulfur, and oxygen, while the detection of sodium elements indicated the presence of another phase that was undesired. The XRD measurement was conducted to confirm it. The existence of dysprosium was spotted in several regions, indicating the successful introduction of dopant material to the matrix. And the presence of carbon after heating at 250 Celsius degree indicated the interaction between ethanol and other molecules of compound used in the synthesis route, likewise the ammonia denoting by the presence of nitrogen. The composition of compounds containing carbon and nitrogen was found to occur as the temperature increased along the calcination process, since both elements were detected only at 250 Celsius degree samples. The phase composition of the powder was analyzed using XRD. The diffraction patterns were stacked for comparison as shown here. Compared to the ICSD pattern list, the sample heated at 250 Celsius degree consists of two major phases of calcium sulfate, are hemihydrate and anhydrate, while the calcium sulfate only found in the anhydrate phase after heating at 650 Celsius degree as expected. The XRD pattern showed the preferred crystal growth orientation of the calcium sulfate crystal was the 002 plan, indicated by the peak at theta of 25.5 degree, and the average crystallite size of the anhydrate phase was about 101.5 nanometers, estimated using SiRes equation by considering the broadening of the most significant peaks. The weight percentage of each phase was summarized in the table based on semi-quantitative analysis. The anhydrate phase after heating at 650 Celsius degree was found with very high concentration, more than 95%, though the thenardite sodium sulfate was found as a mineral phase in both samples. The excess precursors of sodium sulfate remained in the powder due to incomplete washing process before calcination at 650 Celsius degree, and probably formed double salts with calcium sulfate as a solid solution. The elemental composition of the dysprosium-doped calcium sulfate powder was analyzed using XRF. The measurements showed that the atomic concentration of dysprosium to calcium was about 0.7%, more than half of the experimental calculation, that is 1.33%. This result is in agreement with Laxamanans for equal dysprosium concentration given in the wet process. The atomic concentration was calculated based on assumption that the introduction of dysprosium to the base material occurred as a substitutional point defect due to the atomic size factor, since the atomic radii of dysprosium and calcium are quite similar. Both are about 231 nanometers. The glow curve of the powder after irradiation by strontium-90 was shown here. According to the thermoluminescence test, the phosphor exhibited a maximum glow at around 250 Celsius degree. It confirmed the experimental results from previous elder that dysprosium-doped calcium sulfate phosphor has a dominant peak at around 220 until 240 Celsius degree. The phosphor stored 273 microcoulomb from the irradiation and generated about 23 microampere maximum current during the reading. This result indicated a significant improvement of calcium sulfate-based phosphor sensitivity compared to Kartikasari's work for an equal dose. After being annealed at 300 Celsius degree, the powder was read once more, and it turned out that the peak has been emptied at the first reading, indicating only a few electrons were left behind. For the closing statements, we could mention that dysprosium-doped calcium sulfate fine particles were successfully obtained using a wet chemical synthesis route at pH 5, followed by heat treatment from 90 until 650 Celsius degree. And the phosphor dominantly consisted of the anhydrate phase with mass concentration up to 97% based on the semi-quantitative analysis. More than half of the given dysprosium was effectively introduced to the matrix, resulting in a high luminescence intensity which indicated a sensitive phosphor toward a low dose beta exposure, despite the non-uniform particle shape and size. Further work should be dedicated to introducing the pen material more effectively to the matrix and also to obtaining uniform particle size by post-treatment such as grinding and sieving. Obtained TL properties should be supported by thorough investigation, including energy response, fading, and dose dependence of the phosphor to evaluate the material applicability for dosimetry. Thank you for watching.